Okay. So here what happens is when it starts at 0, when load is applied till yield point, this is elastic, and then after some time, and again if loading is continued, it will be in the plastic region. So when it tries to when we try to reduce or reverse the loading cycle, so instead of following this path, so it will follow this path. There is a deformation, plastic deformation between, there is a permanent deformation is there, so that deformation will be there, and it will be, reversal will be happening like this. So this is how the loading and reverse loading cycle happens. So it will start with 0, and it will go to yield point, and then it will go to plastic region. So when it is a reverse loading is happening, the unloading is happening, then it won't go like this, because this is the plastic deformation. So there will be some plastic strain in the model, that is permanent deformation in the model. So that will be there. So the unloading will be happening along this line. So if you see these arrows, it will follow this line. So here basically the one of the important aspect is both tensile strength and compressive. This region it comes under compressive strength. Okay, because we are reversing the load cycle. So tensile loading and compressive loading will be exactly same. Isotropic hardening. Um, Isotropic hardening is often used for large strain or proportional loading simulation. It is usually not applicable for cyclic loading. So isotropic hardening is generally used for large strain or proportional loading simulations, and it is not used for cyclic loading. So this is the important thing. So there is another hardening rule available, that is kinematic hardening. Kinematic hardening allows center of the yield surface to move during work hardening and keeps size of the yield surface constant. So this is another aspect. Okay, one is like in isotropic hardening, center is fixed and surface is allowed to grow. In kinematic hardening, center is allowed to move and surface remains constant. So kinematic hardening should be used for with cyclic loading and conditions to more accurately predict the Bauschinger effect. So Bauschinger effect will be there in the material. So kinematic hardening is generally used for cyclic loading condition. What exactly is the Bauschinger effect? Let us see. Yeah. So the Bauschinger effects is we can see here the tensile strength is greater than the compressive strength. That is in simple terms, it is a it's okay. So Bauschinger effects is like yield stress in tension. In general, yield stress in the tension is greater than the yield stress in the compression. Okay, so this is called Bauschinger effects, and bilinear kinematic hardening is very useful. It should be used for cyclic loading condition. So that is on material nonlinearity. Coming to geometric nonlinearity, we have three nonlinearities. Um, so one is material, geometric, contact, boundary conditions. So these are the three non-linearities which we use in stress analysis. So now let us talk about what exactly is the geometric nonlinearity. If a structure experiences large deformation, its changing geometric configuration can cause structures to respond nonlinearly. So it is characterized by large displacements and rotations. If you see here, there is a fish rod here. Okay, when it is fully loaded, when a fish is caught, so there will be a large deformation in the fish rod. So when you try to plot load versus deflection, the stiffness is always nonlinear. It's not a straight line. The slope is not a straight line. It's a curvature. So this curvature is again depends upon the slope is again depends upon the how much it is loaded and how much it is getting deflected. So so this is very important to capture this nonlinearity in our stress analysis. So why we need to capture the nonlinearity? Okay, in our stress analysis. For example, let us see. Okay, let us see a typical cantilever problem. Okay, let us take a cantilever problem and subject it to point load. And when it is subjected to point load, so generally the load will be applied on the surface. For example, a cantilever, if any cantilever beams, any beams, generally it is subjected to normal to the. If you see here, this is the cantilever beam, and our should be acting this. Okay, but if you try. So load should be acting on the surface, normally. This is the correct representation for a load, typical loading. So this will be taken care when you give non-linear geometric option. Okay. So if you don't account that one, then how the loading will be? So the loading will be. Okay. So the loading is supposed to be like this, but if you don't specify non-linear geometric option, then loading will be something else. So this is the first load step. We applied one load and load is reflected. Okay. Then second load, upon the deformation, load step 1, we apply F1 load, and load step 2, we need to apply F2 load. So if we have a condition saying that F1 load should be, F1 and F2 should be acting normal to the beam cross section, normal to the beam surface. If you give another job, it will be acting like this. Otherwise, it will be acting like this. So there will be a lot of variation. Okay. So it is important to note that orientation of loads and its effect on the structure in large deformation. Suppose in case of acceleration, direction before deflection, direction after deflection. Okay. Similarly, if you apply a load point load, the load is supposed to be acting vertically normal downwards. This is before deflection, and this is direction after the deflection. So if you want to apply further load deflection on this deformed geometry, it can be applied like this only. Okay. So when you try to apply pressure, pressure always acts normal to it. So this will be giving perfect results. So it is very important for us to apply pressure always. If it is not, if you want to apply pressure always normal to surface, okay, load always normal to surface, it is always advised to apply pressure instead of point loads. Okay, so point loads will be acting along the constant directions. Okay, so it is very important for us to understand like how to apply loads. Whether it is a non-linear geometry will be having a significant role in load application. So let us understand so what exactly this analog form. So here, if you see here, this is our fish rod, and it is applied a load like this. Okay. So in this condition, there is a large deformation happening here, and it should be captured. It should be captured using analog option, nonlinear geometry option in our stress analysis. So other things in the geometric nonlinearity are, one is we discussed about large displacements. Similarly, we have rotations and strains, large rotations and strains. So these two things are also by length of the element will give 0.04. Okay, so this comes under large displacements and rotation geometric nonlinearity. So this is under small strain, and this is under rotations. So this we have discussed. So so here geometric nonlinearity, one of the important thing is a stiffness matrix is nonlinear. Okay. This is purely because of geometry. Loading. Okay. So one is because of geometry, one is because of loading. Let us understand one more nonlinearity, that is contact. Okay, also known as change status. One is on geometry, one is on loading, another one is boundary condition. That is contact. So let us understand what is contact. Contact is when two separate surfaces touch each other, that they become mutually tangent, and they are said to be in contact. So when the two surfaces are come into contact, and they mutually become mutually tangent, then they are said to be contact. So this is the contact definition. So one of the important things in the contact is they do not interpenetrate. That means if you see this hemisphere, this component cannot interfere into penetrate into this component. Similarly, this component cannot penetrate into this component. This is actual physics. In actual physics, when two components are come into contact, they won't penetrate into each other. Same thing it has to establish here. Okay, they can transmit only compressive stresses and tangential frictional forces. So and they do not transmit any tensile forces. Okay. So since they don't transfer tensile forces, and they are free to separate. There are two components. When they are doing like this, when they are moving towards like this, there will be compressive forces will be generated. Okay. So when they move away from each other, they won't. So it will generate compressive force. Suppose if they are together, suppose let us assume they are not in contact. Okay, so they are integral, both are integral. Then when you try to move this way, it will generate tensile force, but they are not integral. Okay, they are contact. So what will happen when there is a load happening like this, they are free to move away because nothing is restricting them. So in contact, generally we can see only compressive stresses. We cannot see any tensile stresses. So compressive stresses will be there. Compressive tensile stresses, no. So there won't be any tensile stresses. Only compressive stresses will be there. Whenever there is a whenever the compressive stresses are becoming zero, and then immediately it is free to move away. Okay, the contact will be open. When there is a zero compressive stress, the contact will be become free to separate, or it is open. So let us understand more on contact. So when there is these two are components. So in this status, there is no contact force. There is a gap is visible. So when there is and this component is moved further, then it establishes an initial contact. That will result to a new boundary conditions with contact force. So here there is that when there is no contact, there is no changes in this surface. But when it is resting on this component, when this ball is resting on this component, on this surface, resulting into new boundary conditions. So and when there is a load is applied further, and there will be like further the change in the geometry here. So here it is a point contact. Now it is becoming a line contact here. So boundary condition changing with the deformations. So as the load is applied, there is a deformation is happening. That will be then boundary conditions will be changing. So this is a one type of non-linearity. So here change in the loading conditions will be changing. There will be change in the boundary conditions here. So a contact is generally depends upon deformation as well as loading conditions. So contacts are very useful in our stress analysis. If you see this complex assembly here, this is some gear assembly. So it is very essential for complex assemblies to simulate contacts. So how accurately you simulate the contact behavior will result to accurate simulation of the assembly. So here we have provided some contacts between these two helical gears. Okay, so resulting into a proper the proper simulation of the helical caves. Actually, there are several contacts options in stress analysis, and the majority of the contacts we generally use in our stress analysis, day-to-day stress analysis, is two types. One is surface, one is surface to surface, okay, and another is node to node. Before that, we'll discuss on these two things, okay. They're generally, like, if you see, like, if you want to define any contact, a contact element consists of two one pair. So this location, so either contact, we call it as contact, one is called target. Okay. So vice versa, you can swap also. Okay. So one of the surface is designated as target surface, another surface is designated as contact surface. Contact elements is used to track the location of the contact, enforce contact compatibility, prevents a contact surface from passing through each other. That means if you don't define contact and if you apply the load, this component will get itself. Okay? It won't recognize this surface, it won't recognize this geometry, so it will move forward. Okay, so it is very important for us to simulate a contact here, so that this target or contact will predict this contact and transfer contact stresses between the contact surface. Of course, it will transfer the loading. Okay, so loading between the two assemblies. So friction plays very important role in contact simulations, contact modeling. So tangential or sliding behavior, the sliding behavior between these two things may be like frictionless or friction. Okay, so frictionless behavior allows body to slide related to another without any resistance. There won't be any resistance if you give less between these two components. When friction is included, it will develop shear force between these two bodies. There will be forces generated between two bodies along that movement, tangential direction. So either you can give friction or without friction. Either way you can give it. So in ANSYS, friction is implemented using Coulomb model. Coulomb is a macroscopic model that states that equivalent tangential force Ft transmitted between two bodies cannot exceed a fraction of normal force. So this equation states that the tangential force should not exceed friction coefficient into normal force. If it exceeds, then there will be sliding will happen. Okay, so this normal force, the partial of this normal force should not exceed tangential force. If it exceeds, then this component starts moving. Zero. So contact problems fall into two general classes: rigid to flexible, flexible to flexible. So generally, rigid to flexible states that. So if you see here in for metal forming, so all these components which are involved in forming a metal are rigid, and this material which is undergoes deformation is forming. They are flexible. This is one of the classic examples of rigid to flexible, and flexible to flexible are bolted flanges. Means all are flexible. So both the target here contact is here one of the general contact is defined by a pair of surfaces. So here one pair will be rigid, other pair will be flexible, whereas here all are flexible. So if you see here, this is the bolted joint. Look at how many contacts we have simulated here. We have simulated contacts between two flanges. We have simulated contacts between bolt head and this flange. We have simulated contacts between bolt this flange and nut, and we also simulated contact between bolt and nut. So we are close to four contacts we have simulated. This is a typical bolted joint assembly, and this is the cross section. Node to node. So now, let us talk about node to node. These elements are used whenever a single point will come into contact with a uniquely identifiable point. Okay. So let us take same example. Here, I need to make node same location. I need to make node. So I need to make same location nodes. So in both the components, and this one will be forming into one contact pair. Okay. These elements are used whenever a single point will come into contact with another uniquely identifiable point. So perfectly same location. Okay. It should be uniquely in the same identifiable position. These elements can also used. So this there is no gap. Let us understand there is no gap. For our understanding, I put it in a certain gap. If you see here, there are two flanges here. So there is no gap existing between these two things. But if you see the nodes, they are perfectly aligned. Same location we have nodes. So this is a node-to-node contact. If you make it multiple node-to-node contact, then this will become surface to surface. Like we have taken one surface, we have taken one surface, but multiple of node-to-node can be used as a surface to surface contact. So this requires that you must know exact location of contact beforehand when you create model. So it is very important for us to understand. We should know the exact location of the contact before you do the analysis. Multiple node-to-node elements can be used to model surface contact with two multi-element surface. Same thing. The mesh on each surface must be identical, as I discussed. Like mesh here and mesh there should be identical. Relative sliding deformation must remain small. The sliding deformation, that means deformation along this direction, should be very small. Valid for only small deflection response only. This is valid only for small deflection response only. So that is on node to node. And coming to surface to surface, surface to surface is very widely used in stress analysis. The important thing is it is very user friendly. We can take any arbitrary shapes. Okay. For example, if you see here, this is a ball bearing. So this is very complicated shapes involved. Complicated shapes are there. So here, if you want to go for node to node, it is very tough. So we can take surfaces, approximate surfaces. So and we can create contact pair. Here, exact location of contact need not be known. The two surfaces can have different meshes. That is one of the important advantage of the surface to surface. Here we need to make node to node. We need to make same mesh, whereas in surface to surface it is not required. Relative sliding is supported. Large relative sliding is supported. Large strains and large rotations are supported. Very easy in modeling compared to node element. So if you see compared to node, Surface to surface have majority of advantages compared to node to node. So that completes our any questions? If you don't have questions, then I'll continue for next chapter as well. So we completed fourth chapter now, and we'll proceed for fifth chapter, loads and boundary conditions. So let us look into the another chapter. So in fifth chapter we'll be covering the let us look into the chapters we'll be covering. So we'll be talking about constraints, coupling and constraint equations, and types of loads. So let us let us let us not look into the simulation aspect. Let us on a theoretical aspect or practical as a practically just think about. So suppose let us understand a cantilever, if you don't constrain there, so will it be restrained or without subjecting load also can this model will be held in the space? So definitely it will fall down to earth. Okay. So rigid body motion is similar to that. A rigid structure is free to float in space if there are no boundary conditions. Rigid body motion includes translation and rotation. So it can move this way, or it can move this way, or it can move this way, it can move this way, whatever it may be. Okay. Rigid body displacements are the displacement modes that doesn't cause stresses and deformation. So this type of movement, it won't cause any stresses. So this is the rigid body motion. Rigid body motion is it is free to float in a space if there are no boundary conditions. Let us look into the this final assembly global matrix. F is a force matrix, stiffness, global stiffness matrix, and D is a global degrees of freedom matrix. Okay. So global stiffness matrix of unsupported structure is a singular matrix. So because its determinant is equal to 0. So we in our initial sessions we discussed about this when there are no constraints in the geometry. Okay, the stiffness matrix will become singular, and the resultant the determinant will be equivalent to 0. Okay, so in general the global stiffness matrix assembly is a singular. Okay, you cannot use straight away that singular stiffness matrix to solve our finite element model. So we need to make it we should remove the singularity in the stiffness matrix by imposing the boundary conditions. Okay, if asked software to solve D, it may complain of an attempt to divide by 0, providing an error message related to rigid body motion. So if you try to solve this type of problem without putting any constraints here, then it will give a rigid body motion error. So to remove the singularity, we need to impose the boundary conditions. So error message related to rigid body in some commercial softwares are mentioned here. So in general, in ANSYS, it will give negative main diagonal during solution, small pivots, DOF limit exceeded, negative terms on factorial diagonal, excessive pivot ratios, that is given by Nastran, 2004 exit code, that is given by Mark. In few solution software, the solution will run, but results contain displacements that are very large in one or more directions. So in some softwares, it will give results with very large definitions or displacements. So generally, boundary conditions are two types. This also we discussed sometime back. We can give either homogeneous or non-homogeneous. Homogeneous means which is it is completely constrained. That is, displacements will be zero. Non-homogeneous will be applying a constant deformations or displacements. Instead of u equals to 0, we will apply constant values. So same thing, like if you solve this problem, this is our global stiffness matrix. When you try to make it a determinant of this problem, then it will become 0. It is a singular matrix. Okay. So now you cannot solve this problem with this one. So until unless if you constrain this geometry or this configuration, and then only we can solve it. So here we have fixed here d1x equals to 0. When you try to give equals to 0, that we can easily solve this problem. These things we already discussed. Similarly, if you apply some instead of constraining, if there is a condition saying that there is a constant deflection is there at this point, we can give that factor also here. Instead of equal d1x d1 is equals to 0, we can give uniform deflection as well. So in general, we always should give minimum constraints required. We should not give maximum constraints. Okay, and the minimum constraints means the minimum constraints which will be used to prevent rigid body motion. For example, if you see this 2D spar problem, so when you try to constrain a this model at this location, and when you try to rotate, it is prevented. Rigid body motion is prevented for this type of things. Okay. So here, when you try to apply load, this is a 2D spar, right? When you constrain here at this node, both along the beam length and normal to the beam, and when there is a moment load is applied, it can move. There is a rigid body motion, okay, along this direction. So this can be arrested when you try to restrain another end. Similarly, same is the case with the beam as well. Okay. So in beam, if you can apply, there are two ways you can apply depending upon our loading pattern and simulation beam representation. So these boundary conditions will definitely allow rigid body motion, but here there are two conditions. Okay. So one is cantilever condition, another is simply supported condition. So in cantilever condition, you need to constrain in 3 degrees of freedom. Okay, that is you need to constrain ux, uy, and rho z. Then it is properly constrained. Otherwise, you can also constrain ux and uy, and here uy you can constrain. So this is the minimum constraints you need to give. Coming to 2D models is similar to 2D spar only. So if you try to constrain at one location here, try to solve it, it won't solve. There will be a rigid body motion along this direction. It can rotate. So this rotation can be prevented if you arrest at this point. And coming to 2D axisymmetric, if you don't give any boundary conditions, definitely it will have rigid body motion along this direction. So if you arrest one node, it is sufficient along this axis. So rigid body will be prevented. So on 3D as well, like here we can prevent it by using so 3D will be having 3 degrees of freedom. So this can be constrained in to make it rigid body motion prevented. So one node we need to constrain 3 directions, ux, uy, uz. Second location we need to constrain in 2 directions, ux and uy. And third is left alone thing we need to constrain. So these are the minimum constraints. Some of the examples we have listed out. But in general, we need to whenever you give a boundary conditions, you need to review the results and try to understand whether whatever boundary conditions we have given, they simulate flight physics, they minimize the rigid body motion, they minimize the over constraints. Okay, it should not be over constraint. If it is over constraint, it will result to high stress, or it will give inaccurate results. So in general, translations in all 3 directions, rotations about 3 arbitrary perpendicular axes must be restrained. So whenever if you take any geometry, the geometry should be restrained in all 3 directions and rotations. Okay, means the boundary conditions we need to give such a way that it should not have rigid body motion in 6 directions. 3 translation, 3 translation, 3 rotation. So it should not have a rigid body motion along 3 directions. Excessive constraints are applied to a model and verify frequently. So if you give excessive constraints, always we should look for a results whether they are making sense or not. Excessive constraints are worse than insufficient constraints. The solution will not run with insufficient constraint. Excessive constraints produce incorrect results. So if you differentiate between over constraints or excessive constraints and insufficient constraints, the insufficient constraints always won't solve, but excessive constraint will solve and it may give incorrect results. So it is very important for us to understand whether excessive constraints will make whether the constraints we have given are proper or not. A common model check to verify rigid body motion constraint is to apply uniform elevated temperature to the model. A properly constrained model should not generate any stress under free thermal expansion. So this is very important thing. Okay, so any geometry which is constrained, okay, when you give a uniform elevated temperature, okay, so it should not, it's like a uniform expansion, uniform thermal expansion. In theory, uniform thermal expansion should not cause any stress. Okay, so when you try to apply boundary conditions and you want to check whether this model is properly constrained or not, okay, then apply uniform temperature, run the model and check whether any stress is generated. If stress is generated means the constraints are not proper. So I'm not sure about other programs, but in ANSYS we have a nodal coordinate system. The nodal coordinate system is attached to every node. Okay, by default, nodal coordinate system is parallel to the global Cartesian. Okay, so that is all applied forces, displacement constraints are interpreted in global Cartesian. So let us take a very simple example. Okay, we'll take a cantilever problem. Cantilever problem. Apply load. Okay, of this geometry. I need to apply the vertical load. I need to apply. So how I need to do it? So what? So one of the approach, two approaches. One is you can resolve into this component into this component. So we can apply load. Okay. So this way we can do it. This is one method. There is one more smart method involved. Suppose this is our particular load. I can orient it this way. So what we can do is we can create a one coordinate system. This is our extender. Okay, this is our global extender. So whether if I create one local coordinate system, such as that, so my y is aligned this way and x is aligned this way. This is our system. This is local coordinate system. And we then create one local coordinate system. Such a way that my y is aligned along the load application. So then I can rotate this node along this direction. So when I try to apply FY load, automatically they will be applied something like this. Okay. So this is where we can use this nodal coordinate system. You can refer to ANSYS help to understand more on this nodal coordinate system. So this is used very widely in our stress analysis field. Okay. So you can apply nodal coordinate system for each node differently. If you see here, we are applying nodal. This is all nodes are aligned to the global Cartesian. Then we have a requirement saying that these nodes should be aligned in particular direction. Then we can make it to as per our requirement. So this is they are aligned into Cartesian, global Cartesian by default. So this is the cylindrical coordinate system. So x is represented to radial. So all nodes are rotated into radial coordinate system. So displacement constraints are also used to enforce symmetry or anti-symmetry. Symmetry bases are out of plane displacement and in plane rotations are fixed. Whereas anti-symmetry, in plane displacements and out of plane displacements are fixed. So for example, if we take this I-beam, so this I-beam is perfectly symmetric about this line. So we can model only this component, and this line we can use symmetry boundary, and we can fix everything. Okay. Similarly, anti-symmetry basis also, if the loads are completely reversed, then you can then we can arrest in plane displacements and out of plane rotations. So it's a completely reverse. In symmetric, we can constrain out of plane and in plane rotations, whereas in anti-symmetry, we can constrain in plane displacements and out of plane rotation. So coming to one of the classic problem here, plate with a hole. So as we studied some time back about symmetry, so here we can simulate only 1/4 model. No need to model complementary. 1/4 only we can model it. And what we can do is we need to arrest this phase along this direction. Okay, this phase should be arrested along the normal to this phase. So that is x direction. And here we arrest in the normal to this, that is y direction. So that's how we can impose the symmetry boundary condition. So similarly, like if you see here, this is some hollow disk, some classic example. You can make a note it down. You can solve it at your whatever software you are using. So it is subjected to 5000 RPM. So 5000 RPM, and these are the details, geometry details, um, and RPM is converted into angular velocity, and these are the density material properties we have assigned. So here, so it is very important for us to understand whether whatever boundary conditions we are giving is making sense or not, okay, or it should be constrained, properly constrained, it should not be over constrained, okay. So the for this rotor, for any rotor, uh, to avoid rigid body motion, it should be constrained along axial and circumferential direction. So what we have considered is four nodes we have taken, and four nodes we constrained, four nodes 90 degrees apart. We constrained axial and circumferential direction. Okay, so radial direction should constrain. If you constrain radial direction, then it will be power constraint. Generally, any geometry in the universe, it should be free to expand. So when you try to radial direction, then it will be over constraint. So in this example, I can also tell about node how this one node conditions are used for applying the boundary condition. So what we did is we taken four nodes 90 degrees apart, and we also axial direction. Axial direction means in this direction, four nodes, and also we also along circumferential direction. Circumferential direction is that means tangential direction. So what we can do, what we did is we pick this node and rotated in cylindrical coordinate system. Okay. In cylindrical coordinate system, R means X means radius, Y means theta or circumferential, Z means axial. So we rotated all four nodes in cylindrical coordinate system, and we applied the constraint. And if you see the behavior of this component, deformed versus undeformed, and it is uniformly growing when it is subjected to angular velocity. Okay, and if you see the deflection plot as well, it is uniformly growing from bottom to top. So these things, what we will do is like we'll discuss once we solve the once we complete the loads and boundary loads also, then we'll discuss this case study. But just in brief, like I'll tell you, the maximum stresses observed in hoop and matches with the S1. If you see here, I plotted two stresses. One is S1. S1 is maximum principal stress. Hoop stress is along this one, along tangential stresses. So if you see, both are matches. So these stresses purely developed centrifugal force. That is nothing but density into R into omega square, because it is subjected to uniform rotation. So that's complete today's session. We'll continue tomorrow. Any questions, please raise. So tomorrow we'll be discussing more on loads and boundary conditions. So we completed boundary conditions. We'll be discussing on couplings and constraint equations and loads types of loads. So any questions?